So you'll notice I discovered different colors on my app. Hopefully it doesn't bother you. If it really bugs you and you really have trouble seeing it, you can let me know and I could switch to doing white and black. So I want to talk a little bit about differentiability. That is a big, huge word, but basically if something is differentiable, that means that the derivative exists. So oftentimes functions are differentiable in most places, but then there's one point where it's not differentiable. That happens quite a bit. I'll talk about the cases where it is not differentiable. So we have a theorem, and the theorem is if f is differentiable at x equals a, then it is also continuous at x equals a. But I did write a note. The note is that the converse is not true. What I mean by the converse not being true, I mean that if it's continuous, it's not necessarily going to be differentiable. I'll give you an example where that happens. So we really have only 3 major cases where a continuous function is not differentiable. So first of all, if a function is not continuous, it is not differentiable there. So keep in mind continuous, we do have that definition. We have, we want to have a limit that exists and is equal to the value in order to have something continuous. If it's not continuous, then it's not differentiable. I'm going to actually write that down because that's really, really important also. So I'm going to now give you those 3 cases. So the first case happens if you have a function that has a cusp in it. You're probably not going to see this one very often, but I'll just give you it. Usually I just like to draw a picture, but I figure you'd probably prefer an actual example. You're welcome to graph this on your calculator or on Desmos, and you can even take a look at it. So y equals x to the 2/3. It kind of looks like this. Not a perfect graph. You can graph it on your own if you want, like I said. But it has a cusp at 0, 0. That's what that little weird thing where it goes down like a negative square root function and then up like a regular square root function is the only way I could think of to describe it. That one is continuous, but it actually does not, you can't actually take the derivative of that. Okay, the next one, the corner, this is one that you see a lot. Believe it or not, the graph of y equals the absolute value of x actually has a corner in it, and for that one you're not able to take the derivative of that one at x equals 0. Everywhere, by the way, on these, you can take the derivative everywhere other than the cusp or the corner or the vertical tangent line occurs. So you can see here that this one has a corner. So I'm going to say it's not differentiable at x equals 0. And I'll say the same thing for the cusp. So our third situation where you have something that's continuous but not differentiable is our third situation where we have something that is continuous and not differentiable is when you have a vertical tangent line. Actually, this happens more often than you would think. There's not an asymptote or anything in this one. It is continuous everywhere. But the graph of y equals the cube root of x, or which we also write as x to the 1/3. You're going to probably want to remember that, by the way. That one has a vertical tangent line at x equals 0. So hopefully you remember this from pre-calculus. It looks kind of like y equals x cubed was just rotated and flipped around a little bit. This one has a vertical tangent line at x equals 0. So like the other two, it is not differentiable at x equals 0. Actually, so you'll notice these all occur at x equals 0. That is common for things that are parent functions that haven't been shifted around, but keep in mind that oftentimes we shift around y equals absolute value of x, like we add 3 or add 2 or subtract 8 or whatever. If you do that on the inside of the bars, that will shift it over, and then it'll be not differentiable at a different point. So we have one more case, and that's going to be when you have a point where the derivative on both sides is different. So if you're looking for whether or not something is differentiable, and you have a piecewise function like this one, you are going to have to do several things. The first thing that you should always check for when you're trying to determine if something is differentiable is you should always check the continuity, because we know if it's not continuous, it's not differentiable. So first of all, keep in mind it will be continuous everywhere. We're not 100% sure about 0, but everywhere else it is continuous, because negative x and x don't have anything objectionable in them. They don't have any denominators. They don't have any square roots. There's no logarithms. So we're good on those ones so far. However, we need to check at x equals 0. So first of all, we need to make sure that f of 0 exists. And yes, it does. If we look at that, it gives us 0. We need to make sure that the limit exists. So the limit as x approaches 0 from the left is going to be 0. That's the one that we just checked. This is going to be the right one right here. So the limit as x approaches 0 from the right is also going to be 0. That means that the limit overall of f of x is equal to 0. And that's also equal to f of 0. So it is continuous. So we're good there so far. So we know that that has been satisfied. The next thing we need to do is we need to determine whether or not it is differentiable. So in order to do that, we need to find f prime of x. In order to find that, we have to do our two derivatives separately. So we're going to do that right now. So our first one ends up being -1. The second one we're going to do is going to be same idea, and that ends up being 1. So we have 1, and this one up here was -1. Now, honestly, you're not going to be doing the difference quotient every time you do this in the future. It'll be a lot easier. I think the next video is where I'm going to show you how to find the derivative quickly, and you'll just be able to see that the derivative of -x is -1, derivative of x is 1. You might also be able to figure that out just by thinking about what the graphs of it look like. Like the graph of y equals -x has a slope of -1. Slope of the tangent line is just going to be -1. Same thing, y equals x has a slope of 1. So now that we have found the derivative, we need to determine if the derivative from both sides is the same. You might be able to see that it's actually not, but I'll show you using limits. So the limit as x approaches 0 from the negative side of f prime of x of our derivative is equal to -1. The limit as x approaches 0 from the positive side is equal to +1. Therefore, the limit of the derivative does not exist, so our function is not differentiable. And that's going to be only at x equals 0, by the way. By the way, just a side note, you may or may not have realized this, but this graph right here, if you actually graph it, it looks like this. That's equivalent to the absolute value of x. So that's just a kind of a side note. So you kind of can see that we had oftentimes it's the point where the derivative on both sides is going to be different is actually going to be because it has one of these three things. So there's going to be a few ways to find it. If you have a graph, that's great. If you don't have a graph, then you can also find it algebraically like we just did.